So we are here for our last example on lateral and horizontal displacement, and it's saying light consisting of blue and red light is incident in air glass interface. The two colors emerges from glass block at 2 points P and Q respectively. So if I can involve some simple drawing in what we are saying. Okay, so we are saying that if the light is incident, is that okay? White light, and what happens is they are saying that they are moving out at the point I can do that, and then I can do that. This is P, Q. And maybe this is A, this is O, isn't it? So the light, there is red and blue. So I can say this is the blue light, and maybe this is the red one. Is that okay? So they're saying that the refractive index for if the speed of the blue and red light are at this and that respectively, what is this? This is P, Q. So I can say this is the refraction for blue, and then this is the angle of refraction for the red. Maybe I can do like that. So now to solve this problem here, they have consisting of light consisting of blue and red light is incident in air glass interface. The two comes out from these 2 points. So what is very important here is to first of all get this distance here. I should get this distance, and I get this distance, and then at the end I subtract the two. If I know this, I know this, but do I actually know the refractive index? The refractive index can be gotten by saying speed of light in a vacuum to the speed of light in air. Okay? So if I now get the refractive index, please, this distance here is supposed to be 5 centimeters. It is given to us as 5 centimeters, and this angle is 60. Before we begin, so this is 5, this is 60. So as I've been saying, let's go now towards our calculation. We shall say that for red, let me begin with for blue light. Applying Snell's law. At O. And then I will say for blue light, I'll now say it is from air, refractive index of air times sine of angle in air should be equaling to, actually I should first calculate the refractive index by saying that refractive index equaling to speed of light in a vacuum to speed of light in a glass. So that means that any B can be equal to speed of light in a vacuum is 3 exponent 8 divided by speed of light and that is now we're talking about below. For below is 1.88 exponent 8. That is the 3 divided by, that is 3 divided by 1.88, and that is 1. I can say 1.6 approximately. So I can record it as 1.6 as the refractive index. And then I can say, now if I apply Snell's law, I'll now say refractive index of air is 1, even if I go direct, 1 times it. And me right, don't jump a step, equaling to any glass sine of R. So that means that air 1, sine of angle in air is sine A 60. Refractive index of the glass is 1.6. Sine of the angle of refraction for blue. So that means my RB is the same as the sine inverse of sine 60 divided by 1.6. Okay, so I can say sine 60 divided by 1.6. Then shift sine inverse of the angles. This is giving me 32.8 degrees. And then I can say from triangle AOP, we shall say now what is tan of RB will be equal to opposite over opposite adjacent out of 5. So that means that my tan 32.8, it is 32.8 equaling to AP out of 5. AP equaling to, and then let me see, and then times 32.8. 32.8. We are saying that it is 5 times tan of 32.8. That is the same as 3.222 centimeters. And then we can now get for red light. For red light, what is the refractive index? Speed of light in vacuum, which is 3 exponent 8 divided by the speed of red is 1.94 exponent 8. What does that tell us? It is now 3 divided by 1.94. That is 1.55. So if I apply Snell's again also at that point, I'll say refractive index of air, which is 1 times sine of angle in air. So I'm now looking for red. Sine 60 equaling to refractive index for the glass for the red light, and then sine of angle of red light. Is that okay? So what will be my R? My R is going to be the sine inverse of sine 60 divided by 1.55. 1.55 to get now that to get R. So I will therefore say it is sine 60 divided by sine 60 divided by 1.55. Okay. What is happening here with the calculator? Let me see. And then divide by 1.55. I'm getting that. And then shift sine inverse of the answer to get 33. I'm getting here if this one has 33.96. 33.96 degrees, almost 34. So I can now say from my triangle AOQ, this triangle here, I'm getting what is that. I can say tan of RR equaling to, if I look at this angle here, is equaling to opposite, which is the AQ of the adjacent, which is 5. That means the tan of 33.96 is equaling to AQ out of 5. What is the AQ? So I can say tan of 5 times tan of 33.96. That is 3.37 centimeters. So we shall say that AQ is equaling to AP plus PQ. So PQ will be minus, so you can see now 3.37 equaling to AP, but remember AP is 3.222 plus PQ. So my PQ, this distance, because I've calculated this, I've calculated that. So I get the difference between the two. Minus 3.222, and then that is equal to 0.4145 centimeters. So that means that the horizontal displacement in this kind of problem PQ is equivalent to this value. We first calculated this, we calculated that, and now subtracted to see how the two separated. So thanks for listening. Let's meet in the next part of our lesson.